Study in Chapter 4 on matter continues with Lesson 2, the changes of state. I'm on page 107 in your textbook, and in the right-hand section, the what you will learn says that students will define and compare thermal energy and temperature. Students will relate changes in thermal energy to changes of state, and students will explore energy and temperature changes on a graph. Page 107, thermal energy and heat. Shards of ice fly from the sculptor's chisel. As the crowd looks on and a swan slowly emerges from a massive block of ice, as the day wears on, however, drops of water begin to fall from the sculpture. Drip by drip, the sculpture is transformed into a puddle of liquid water. What makes matter change from one state to another? To answer this question, you need to think about the particles that make up matter. Energy. Simply stated, energy is the ability to do work or cause change. The energy of motion is called kinetic energy. Particles within matter are in constant motion. The amount of motion of these particles depends on the kinetic energy they possess. Particles with more kinetic energy move faster and farther apart. Particles with less kinetic energy move more slowly and stay closer together. The total kinetic energy and potential energy of all the particles in a sample of matter is called thermal energy. Thermal energy, an extensive property, depends on the number of particles in a substance as well as the amount of energy each particle has. If either the number of particles or the amount of energy in a particle changes, the thermal energy of the sample changes. Within identical sample sizes, the warmer substance has the greater thermal energy. In Figure 7, the particles of hot water from the hot spring have more thermal energy than the particles of the snow on the surrounding ground. Thermal energy is the total energy of all the particles in a sample of matter. The total energy is added up the kinetic energy, the movement of those particles, and then the potential energy, the lack of movement of those particles. But it is the total kinetic and total potential energy of all particles in a sample of matter. Page 108, temperature. Not all the particles in a sample of matter have the same amount of energy. Some have more energy than others. The average kinetic energy of individual particles is the temperature. Notice the difference between those two. Thermal energy is the total energy of all particles. The average kinetic energy is temperature. A little bit of a difference. The average kinetic energy of the individual particles is the temperature, an intensive property of the substance. You can find an average by adding up a group of numbers and dividing the total numbers of the atoms in a group. For example, the average of the numbers 2, 4, and 8 and 10 is 2 plus 4 plus 8 plus 10. You divide that by 4 because there's 4 different numbers that you're containing, and 6 is your average. Temperature is different from thermal energy because thermal energy is the total and temperature is an average. You know that the iced tea in the picture above is colder than the hot tea in Figure 8. Stated differently, the temperature of iced tea is lower than the temperature of hot tea. You also could say the average kinetic energy of the particles in the iced tea is less than the average kinetic energy of particles in the hot tea. So it's using this hot and cold example to show you how temperature is a measurement of those movement of particles, and it's the average movement of those particles. Heat, the third item that we're comparing today, heat is when a warm object is brought near a colder object, thermal energy will be transferred from the warmer object to the cooler one. The movement of thermal energy from a substance at a higher temperature to one at a lower temperature is called heat. When a substance is heated, it gains thermal energy. Therefore, its particles move faster and its temperature rises. When a substance is cooled, it loses thermal energy, which causes its particles to move more slowly and its temperature to drop. A really good way to think of heat is when you're cooking something. In cooking, you're trying to heat something up, or you're trying to increase the thermal energy of that substance so it gets to a level to where it's completely cooked and therefore you can enjoy it. When you're done cooking something, what often happens? It cools down. People will say, well, hurry up and eat, otherwise your food's going to get cold. So heat is this movement of thermal energy from a substance with a higher temperature to one with a lower temperature. Heat is usually going from something that is higher energy to something that's lower energy. You yourself probably like to be at a low energy state, hence why you'd rather be sleeping than doing class right now. A lot of things in our world operate in that same way. They'd rather be at a position of rest than in this position of high energy. Particles that are moving, that have kinetic energy, want to be at rest as well. So here's how heat operates. It goes from higher temperature to lower temperature. Next page, specific heat. As you study more science, you will discover that water has many unique properties. One of these in the amount of heat required to increase the temperature of water as compared to other substances. The specific heat of a substance is the amount of heat required to raise the temperature of 1 gram of that substance by 1 degree Celsius. Substances that have a low specific heat, such as most metals and the sand in Figure 9, heat up and cool down quickly because they require only small amounts of heat to cause their temperatures to rise. A substance with a high specific heat, such as water in Figure 9, heats up and cools down slowly because a much larger quantity of heat is required to cause its temperature to rise or fall by the same amount. Specific heat is the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. I have here a picture of Bradford Beach, and maybe you have been down to Bradford Beach, right on Lake Michigan here in Milwaukee. The reason why I have this as an example is because maybe you've been there and you've noticed that as you're at your house or as you're in a different part of Milwaukee in the summertime, it's really, really hot. But as soon as you get down to the beach, it actually is quite a bit colder. Now, why is that? Well, Lake Michigan is really, really big, and it is really, really cold actually in terms of the overall temperature. The water temperature is usually much cooler than the air. Well, that's because water has a high specific heat capacity. It takes a ton of energy to heat up water. Land right next to it, like the land that you're on when you're at home or in the city or even on the beach, has a low specific heat capacity as it heats up. Sand will get really, really hot on the beach even though the water is extremely cool. Now, if you've traveled down to Bradford Beach in the summertime, it can be hot away from the beach. As soon as you get down there, it's cool. That's because the water is cool. The water has this high specific heat capacity. It takes a ton of energy to be able to heat that up. On the next bottom of that page, 109, changes between solid and liquid state. Matter can change from one state to another when thermal energy is absorbed or released. This change is known as the change of state. The graph in Figure 11 shows the change in temperature as thermal energy is gradually added to a container of ice. Melting. As the ice in Figure 11 is heated, it absorbs thermal energy and its temperature rises. At some point, the temperature stops rising and the ice begins to change into liquid water. The change from the solid state to the liquid state is called melting. The temperature at which the substance changes from a solid to a liquid is called the melting point. The melting point of water is 0 degrees Celsius. The melting point is also 32 degrees Fahrenheit, or freezing point at the same time. Amorphous solids such as rubber and glass don't melt in the same way as the crystalline solids. Because they don't have crystal structures or break down, these solids get softer and softer as they are heated, as you can see in Figure 10. So some solids, when they're melting, are going to turn into the liquid state at a specific point. Others are going to simply get softer and softer and softer to get closer to that liquid state. There isn't an exact point. That's the difference between a crystalline and an amorphous solid and when it's heating up. Freezing. The process of melting a crystalline solid can be reversed if the liquid is cool. The change from the liquid state of a solid is called freezing. As the liquid cools, it loses thermal energy. As a result, its particles slow down and come closer together. Attractive forces begin to trap particles and the crystals of a solid begin to form. As can be seen in Figure 11, freezing and melting are opposite processes. Depending on if there's more thermal energy being added or thermal energy is being decreased, you have either melting or freezing that's happening at that same point. The temperature at which a substance changes from a liquid state to the solid state is called the freezing point. The freezing point of the liquid state of a substance is the same temperature as the melting point of the solid state. For example, solid water melts at 0 degrees Celsius. Solid water, that's ice, melts at 32 degrees Celsius, above 32 degrees Celsius, and liquid water freezes at 0 degrees Celsius, or 32 degrees Fahrenheit. So at 32 degrees, you've got the freezing point and melting point. If it's going to get warmer than 32 degrees, ice and snow, they start to melt. If it's going to get cooler than 32 degrees, that's a point where things start to actually freeze. So those two parts are synonymous. They're at the same exact point. During freezing, the temperature of a substance remains constant while the particles in the liquid form a crystalline solid. Because particles in a liquid have more energy than particles in a solid, energy is released during freezing. The energy is released into the surroundings. After all the liquid has become a solid, the temperature begins to decrease again. Here's an example of what they're talking about in Figure 11, and you can also see this on page 110. It's visualizing the states of matter. In this, it's showing you freezing, melting, and vaporization on this scale. So here you have, when the scale is rising or falling, this is a measure of the temperature or the thermal energy that an object has. When something is a solid, it's going to melt at one point and then turn into, if something's a solid, it's going to melt and turn into a liquid. If something is a liquid, it's going to boil and turn into a gas. So you've got this transition that's happening between a solid, when it melts, turns into a liquid. Here's where the melting point and the freezing point are exactly the same. Once it's a liquid, then it's going to at some point boil when it has more energy and turn into a gas. This depiction just shows how these three states of matter change at these specific points. We've got boiling points between liquids and gases. We've got melting points between solids and liquids. We'll talk a little bit more about that change between a liquid and a gas that happens here and how we have what would be vaporization or a boiling point to consider. Changes between the liquid and gas on page 112. After an early morning rain, you and your friends enjoy stomping through the puddles left behind. But later that afternoon, when you head out to run through the puddles once more, the puddles are gone. The liquid water in the puddles change into a gas. Matter changes between liquid and gas states through vaporization and condensation. Vaporization. As liquid is heated, its temperature rises until it reaches 100 degrees Celsius. At this point, liquid water changes into water vapor. The change from a liquid to a gas is known as vaporization. That same degree temperature in Fahrenheit, 100 degrees Celsius, is equal to 212 degrees Fahrenheit. That's our boiling point for water. You can see in figure 11 that the temperature of the substance does not change during vaporization. However, the substance absorbs thermal energy. The additional energy causes the particles to move faster until they have enough energy to escape liquid as gas particles. They're saying when this boiling point happens and when this freezing and melting point happens, there's actually not a change in the overall temperature. It stays at that point, just depends on what direction that thermal energy is moving. If it's decreasing, it's changing into a liquid. If it's increasing, it's changing into a gas right at that exact boiling point or condensation point. Here we're talking about vaporization, so it's from a liquid turning into a gas. Two forms of vaporization exist. Vaporization that takes place on the surface of a liquid is called boiling. When a liquid boils, bubbles form within the liquid and rise to the surface, as shown in figure 12. The temperature at which the liquid boils is called the boiling point. The boiling point of water is 100 degrees Celsius or 212 degrees Fahrenheit. Vaporization that takes place at the surface of a liquid is called evaporation. Evaporation, which occurs at temperatures below the boiling point, explains how puddles dry up. Imagine that you could watch individual water molecules in a puddle. You can notice that the molecules move at different speeds. Although the temperature of the water is constant, remember the temperature is a measure of the average kinetic energy of molecules. Some of the fastest moving molecules overcome the attractive forces of other molecules and escape from the surface of the water. So the two forms of vaporization that exist, one that is below the surface is boiling. For example, you see this coffee pot that's depicted on the bottom of page 112. That's figure 12. It shows that the bubbles are coming from the bottom of that liquid and rising to the surface where that vaporization is taking place. Vaporization that happens just on the surface is called evaporation. Location of molecules on page 113. It takes more than the speed for water molecules to escape the liquid state. During evaporation, these faster molecules also must be near the surface, heading in the right direction, and they must avoid hitting other water molecules as they leave. With the faster particles evaporating from the surface of a liquid, the particles that remain are cooler ones. Evaporation cools the liquid and anything near the liquid. You experience its cooling effect when perspiration evaporates from your skin. So humans have this ability when we get ourselves heated up and our body temperature increases to cool ourselves so that we're not overheating. We start to sweat. And when that sweat that's on our skin evaporates, it actually cools us off because that thermal energy is leaving our body, leaving us cooler. That's a natural way in which this evaporation works, and it actually allows us to maintain our body temperature so that we don't overheat or exhaust ourselves. Condensation, page 113. Pour a nice cold glass of lemonade and place it on a table for a half hour on a warm day. When you come back to take a drink, the outside of the glass will be covered with drops of water, as shown in figure 13. What happened? Did the water from the inside or the lemonade from the inside get to the outside? Well, of course not. As a gas cools, its particles slow down. When particles move slow enough for their attraction to begin and be brought together, droplets of liquid form. This process, which is the opposite of vaporization, is called condensation. As a gas condenses to a liquid, it releases the thermal energy it absorbed to become a gas. During the process, the temperature of the substance does not change. The decrease in energy changes the arrangement of particles after the change of state is complete. The temperature continues to drop as you saw in figure 11. When energy change occurs during condensation, you've got thermal energy that is being absorbed and it's becoming a gas. As a gas condenses to a liquid, it releases the thermal energy it absorbed to become a gas. During this process, the temperature of the substance does not change. The decrease in energy changes the arrangement of particles. After the change of state is complete, the temperature continues to drop as we can see. Reading check on page 113. What energy change occurs during condensation? Well, during condensation, a gas releases energy as its particles become more ordered. Those gas particles have a higher energy than the liquid, and when they're releasing that energy, they're then going to have less energy and become a liquid. They are condensing to form this change from a gas to a liquid. They're forming into a liquid from the gas, so it's releasing that energy. Condensation forms the droplets of water on the outside of your glass of lemonade. In the same way, water vapor in the atmosphere condenses to form the liquid water droplets in clouds. When the droplets become large enough, they can fall to the ground as rain or other types of precipitation. Changes between solid and gas. How do we skip between that liquid state? How do we go from a solid straight to a gas? Well, there's a way in which it's described in science. Let's read about it. Some substance can change from a solid state to the gas state without ever becoming a liquid. During this process, known as sublimation, the surface particles of a solid gain enough energy to become a gas. One example of a substance that undergoes sublimation is dry ice. Dry ice is the solid form of carbon dioxide. It often is used to keep materials cold and dry. At room temperature and pressure, carbon dioxide does not exist as a liquid. Therefore, as dry ice absorbs thermal energy from the objects around it, it changes directly into a gas. When dry ice becomes a gas, it absorbs thermal energy from water vapor in the air. As a result, the water vapor cools and condenses into liquid water droplets, forming the fog you see in figure 14. That change from a solid to a gas is called sublimation. And the best example is dry ice, which is solid carbon dioxide. So it's the breath that you breathe out. So take a breath. That's CO2 that you're breathing out. Turn that gas into a solid, it's called dry ice. It has a really, really, really low temperature. It's actually colder than ice itself, and you can maybe even buy it at your local grocery store, and it has quite a bit of cool properties. If you put it in your cooler below your ice will never melt because the ice is having that thermal energy kept in place by the dry ice. You can also do some really cool science experiments. If you want to do some searching on YouTube, look up dry ice science experiments. That should help you complete the reading portion from what is Chapter 4, Lesson 2. Let's make sure we go back and take a look at the self-check at the bottom of page 114 to make sure we've got an understanding of these changes of state. Number 1 says, describe how thermal energy and temperature are similar and how they are different. Well, we're going to use a Venn diagram to do that. In the Venn diagram I have pictured here, it says each phrase is going to be identified as something that is considered thermal energy, temperature, or both, because we want to understand the difference between thermal energy and temperature and thermal energy and heat. Thermal energy is the total energy of particles, and it depends on the number of particles. They're both similar, thermal energy and temperature. They involve the kinetic energy of particles, and temperature is really specifically focused on the average energy of particles. So the difference is between total and average. They're both talking about kinetic energy, the movement of those particles, but there's a difference between them being added up totally and the average being taken. Let's take a look at the rest of our questions. Number 2 says, explain how a change in thermal energy causes matter to change from one state to another. As thermal energy changes, the kinetic energy of the particle changes. If their kinetic energy increases, particles can overcome the attractive forces holding them together. If their kinetic energy decreases, particles can become subject to forces pulling them together. So your examples of 2 types of energy changes when a thermal energy is changing are your boiling point and freezing point, your melting point, and your condensation point. Those are a number of examples of how that thermal energy is increasing or decreasing, and you have that change of state that's happening at that exact point. List the 3 changes of state in which energy is absorbed. Energy is absorbed in melting, energy is absorbed in vaporization, and energy is absorbed in sublimation. You have them going from a certain state to another state in which energy is being absorbed. It's changing to that state because there's more thermal energy, there's more movement of those particles. So from a solid to a liquid in melting, from a liquid to a gas in vaporization, and from a solid to a gas in sublimation. So anytime there's thermal energy that's increasing, that's being absorbed in that case. Number 4, describe the 2 types of vaporization. Boiling occurs when particles below the surface of a liquid change to a gas, and evaporation occurs on that surface when those particles are moving faster than other particles in that liquid. Number 5, think critically. How can the temperature of a substance remain the same even if the substance is absorbing thermal energy? The temperature remains the same because the absorbed energy is being used to break those attractive forces between the particles of the substance as that change of state happens. So here's where you have the difference between your freezing point and melting point, your difference between your vaporization and condensation. That change of state is happening because that energy isn't going into raising or lowering the thermal energy, it's actually going into breaking those attractive forces between the different types of material, whether you have liquid, solid, or gas. That should hopefully help you prepare and complete your reinforcement. Thanks for following along.